Jean-Baptiste Fourier created the Fourier series to approximate any curve by sines and cosines. Now, it's important to understand that this advanced mathematical technique is often used in physics, engineering, and a variety of other disciplines. And in today's video, we're going to be deriving it. To understand the Fourier series and to derive its solutions, we must follow 3 steps. The first step is to identify all of the characteristics of the Fourier series. The second step is to identify any trigonometric functions and trigonometric identities that will be useful when we actually derive its solution. And the last step is to derive its solution. So let's begin by talking about the expansion for the Fourier series that we will be using in this video. We will be using the expansion f of x is equivalent to a naught over 2 plus the summation as n equals 1 to infinity an cosine nx plus n equals 1 to infinity bn sine of nx. So this is a general expansion we will be using in this video for the Fourier series. Notice that there are other versions of the Fourier series, but we will be using this version. So what is the purpose of the Fourier series? The purpose of the Fourier series is to take any function and any curve on that function and approximate it using sines and cosines waves. In doing so, we can take any function at any bounds on that curve and we can write it in a more mathematical expression that we have an intuition for, because sines and cosines usually come before we take differential equations in calculus, because trigonometry is usually taught before that. Hence, we gain a better intuition for it, and when solving differential equations, we often use Fourier series for that. We often have a better understanding of this expansion, rather than just a whole different mathematical language. Okay, now that we've talked about its purpose, let's talk about some of its characteristics, or some of its terms. So the Fourier coefficients is what we want to solve. The Fourier coefficients. These are a naught, an, and then bn. Now, we also have this summation over here. These summations indicate that there is an infinite amount of terms, which makes this a series. Last but not least, as you can see, x is our main variable. Now, this is an important thing because there's a lot of coefficients, there's a lot of variables essentially in this, because we have variables for coefficients, we have n for another variable, and we have so much other things. So x is our main variable. So that's something that we want to identify. Okay, so these 3 characteristics might not be all of the characteristics of the Fourier series, but it's some of the characteristics we do need to know in order to find the solutions to the Fourier coefficients. Okay, so now that we've talked about that, let's continue by actually identifying some trig identities that would be useful for our derivation. The first one is going to be the integral from 0 to 2 pi of sine of mt multiplied by sine of nt dt. Now, the reason I'm writing this in the terms of t is to indicate that this is general when we have this specific case. This is going to be equivalent to pi if m equals n and 0 if m does not equal n. I want to make a relation to this. This sounds like the Kronecker delta. The Kronecker delta is this symbol. Now, this is often used in quantum mechanics, and the Kronecker delta of mn states that we have 0 if m does not equal n, and 1 if m does equal n. So as you can see, it portrays some similarity to this over here and the Kronecker delta. So this is our first identity that we have to notice. Now, second identity is going to be this. We're going to change this to cosine. We're going to change this to cosine. In doing so, we get the same results. So this is the second identity. Last but not least, we have sine of mt times cosine of nt. And this is going to always be equivalent to 0. And this is our third identity. So these three identities are going to help us drastically when we're going to try to derive the solutions to the Fourier coefficients, which are a0, an, and bn correspondingly to the constant term, and then after cosine and sine. Okay, so now that we've talked about this, let's actually start deriving the solution. So now it's important to realize that we have to tune our mind back to the terms of x because we just used the terms of t to identify that it's a general case. Okay, so what we're going to be doing is a very, very smart thing. We're going to be taking f of x and we're going to be integrating it from 0 to 2 pi. And we're going to multiply it by sine of mt. So we're doing the same thing on both sides. We have equality. We have a0 over 2 plus n equals 1 to infinity, an cosine of nx plus sum n equals 1, infinity, bn sine nx. And we're going to multiply all of this by sine of mx dx. Notice that this also has to be x, and we're differentiating it with we're integrating it with respect to x. So we have to write a dx. Okay. So we've got this dense integration equation, and you might be thinking, how are we going to solve this? Notice that we have to recall once again that we're in the terms of x. So if you have something write a t, change it to an x. Okay. So we have this huge integral equation, but we can solve it pretty easily. We're not going to do anything to the left-hand side, or in your terms, the right-hand side, but we're going to be manipulating a lot of things on the left-hand side. So what we're going to be doing is we're going to be taking the integral from 0 to 2 pi, and we're going to be trying to keep this in preservation and manipulate this. But when you try to manipulate this, you're going to be like, oh, this is very hard to manipulate. And indeed, we're not going to manipulate this, but rather we have to manipulate this side of the equation. And by doing so, we can immediately get a solution. Think about it. If we have a series of sine of nx terms, sine times sine of nx terms, n is equivalent to m in only one case, which means that we're obviously just going to get bn times pi for this. Similarly, since sine, cosine, these cancel out to become 0. And this, obviously, when we multiply this by sine of mx, and we're going to integrate it by its period, this is going to become 0. So we'll get bn pi. So we have the integral of 0 to 2 pi is equivalent to f of x sine mx dx. And this is equivalent to bn pi. Now we can divide by pi, and we get bn is equivalent to this. So therefore, we've solved the Fourier series. We've gotten a solution to one of the Fourier coefficients. And you might be thinking, oh, we've got one solution to the Fourier coefficient. Does that mean the rest of them are going to be easy? And many of you probably think, no, this is the Fourier series. It's going to be hard. But using the identities, we can immediately interchange sine of x and cosine of x and get a sub n. And I'll show you that after we write the solution to bn. So we'll write over here, bn is equal to 1 over pi times the integral of 0 to 2 pi of f of x times sine of mx dx. Second is a of n. So what is a of n? Well, If we do the same thing, we have the integral from 0 to 2 pi of a naught over 2 plus the summation n equals 1 infinity an cosine of nx plus the sum n equals 1 to infinity bn sine nx, and we're going to multiply this time by cosine of mx. Now when doing so, these cancel, and over here we have one case where m is equal to n, so this just becomes an pi, and this, obviously, same rule, still integrating over the period. Now remember, dx, this cancels, so we have an pi, and remember, doing the same technique again, we obviously can just get an to be equivalent to 1 over pi times the integral of 0 to 2 pi f of x times cosine of mx dx. So therefore, we've solved for two of the Fourier coefficients very easily. And you might be stuck right now. How do we solve for a naught? Because for a naught, if we cancel these, we're also going to cancel this. And you might be wondering, how? But then again, we have another smart trick right at our hands. When we integrate this, let's write it once again. 2 pi and then 0. And we have plus n equals 1 to infinity an cosine of nx plus the summation of infinity n equals 1 bn sine of nx. But the smart thing to do is just integrate it with respect to x. Now, that's the real thing. When we integrate with respect to x, let's just see what happens. Because in mathematics, most of the time, we just try to test things out. We try to test things, we plug, we chug, and then we get some creative solutions. We get some characteristics that once we identify, we apply them and we see that there's a unique solution to it. Similarly, let's just try it. If we do, we see that when we integrate over its period, this cancels, but since this doesn't have a trigonometric function because we're just integrating it without multiplying anything, this indeed just becomes left alone. So we're going to have the integral of 0 to 2 pi dx, and we get a naught over 2, and since we're integrating with respect to x, we get a naught over 2 0 to pi, and then we have, since we're integrating with respect to x, we have to put an x over here, and when we do, we get 2 pi a naught over 2, which will get pi times a naught, and then when we plug in 0, this becomes 0, this becomes 0, so therefore pi a naught is our answer, a naught pi, and therefore we get a naught be equivalent to 1 over pi times the integral of 0 to 2 pi times f of x dx. Now you might be wondering about this last step. How do we do this? Well, you probably know that this gets canceled because we're integrating over its period. And this, since it doesn't have any trigonometric function multiplied this time, we do the regular integration things for a constant. We get a naught x over 2, and then we have to do 2 pi 0. And when we plug in 2 pi, we get 2 pi a naught over 2, which is pi a naught. And when we plug in 0, this becomes 0. So therefore, we get pi a naught. So therefore, we get this, and this is going to be our answer for all the Fourier coefficients. Let's just check a naught one last time, because a naught over 2, when we integrate this, is just going to become a naught x over 2, because this is a constant. A naught x over 2, evaluated at 2 pi, will be 2 pi a naught over 2, which will cancel, so we get pi a naught. And then when we plug in 0, everything cancels. So pi a naught is indeed correct. Therefore, these are our solutions to the Fourier series. Now, in mathematics, I believe that there are two ways to solve a problem. One, identify some of the cool characteristics of the problem intuitively, inherently, and then identify some of your own characteristics, combine them both together, and then solve it. That's the thing, because if we didn't know about the sine of mx times sine and times cosine of mx and vice versa, and for all the trig identities, this would have been almost impossible to solve because we would have been stuck looking at this huge integral. But knowing those three trig identities, easily we solved them. Or there's another way you could do it. You could do it by classic algorithmic approaches and just plug and chug, using previous invented methods and plug it in. And I said 2 methods, but there's actually 1 extra method after this. The last method is to invent your own techniques in mathematics, build upon previous methods obviously, but invent it, apply it, it works, and then boom, you find your solution. So those are the 3 methods that I believe you can find your solution. And now that we've talked about finding solutions to the Fourier series, we can make this video to an end. In the next video, we'll talk about applying Fourier series to different types of problems, because that's the most important part. We want to solve for the Fourier coefficients using these formulas, take those Fourier coefficients, and plug it back into the equation. Now that we talked about that, we can make this video to an end. If you like this video on Fourier series and deriving it, please like this channel and subscribe.